In this chapter, we will talk about reaction rates and reaction rate laws. So what is a rate? A rate is how fast something occurs. It typically has units of whatever is occurring over a unit of time. An example of this is the rate of travel, or speed, which would have units typically of like miles per hour, kilometers per hour, meters per second, some unit of distance divided by time. Another example is RPM, like you would have in a vehicle. That is revolutions per minute. So, on the top you have your something, and on the bottom you have the unit of time. This is going to be the same for any type of rate. In chemistry, we are typically interested in how concentrations change with time. So concentrations most of the time are going to be in moles per liter, and so our units for reaction rates are going to be moles per liter times seconds, or moles on top with liters on bottom and seconds on bottom. Essentially, our changing concentration, the thing on top is concentration, moles per liter, and the thing on bottom is going to be change in time. We will be using square brackets to represent concentration in terms of moles per liter. This will be our primary unit for concentration. Rates are the measure of how concentration changes over time. So it would be the change, delta, change in square brackets tells us that we're dealing with concentration. So it's the change in the concentration, in this case of component A, over our change in time. This is essentially a relative rate. Relative rates are the rate of consumption in terms of reactants, or the rate of formation in the term of products. It is related to their stoichiometric coefficients. We will talk about this in our next slide. We have two different types of reactions. We have homogeneous reactions and heterogeneous reactions. Homogeneous reactions are ones in which all the components are in the same phase. So that would be where everything is a solid, everything is a liquid, everything is a gas, or everything is aqueous, meaning that it's dissolved in water. The units will typically be moles per liter per second, or something similar. Could be moles per liter per hour, moles per cubic meter per second. Essentially, a unit of measurement number-wise in terms of like moles or molecules, a volume, liters, square, cubic meters, something like that, and seconds or minutes or hours, depending on your time frame. But always it's going to be some form of concentration divided by time. Heterogeneous reactions are similar to homogeneous, except they will have two or more phases of components. So a heterogeneous reaction would be one in which two or more of the reactants are in different phases, such as the interaction between a gas and a liquid. One of the components would be in the gas phase, the other component would be in the liquid phase. When you have two phases, they're typically going to meet at the interface. That is the location where the two meet. So if you're thinking of like a gas interacting with a liquid, they would be interacting at the top of the liquid, where the gas molecules and the liquid molecules can interact with each other. Another common example is like a solid-liquid interaction. So you could think of taking a solid component, putting it into liquid, and having the interaction occur at the surface of the solid, where the two components are able to interact. So if we're talking about reaction rates and those being measured in terms of concentration over unit time, one of the things that we're going to be interested in is how does the reaction rate compare to how fast the concentrations of our components are changing. Now, how fast the components are going to change depends on the reaction that we're looking at. So let's say we have a reaction that is A plus B goes to C plus D. And let's say that this reaction is occurring at 1 reaction per second. Right? So essentially it's going across our arrow here at 1 revolution per second, right? Every second, the reaction is occurring 1 time. So what we'll find is that our concentration of A, our change in our concentration of A, right, in terms of how fast this is occurring, our concentration of A is going to be going down, right? Because each time the reaction occurs, we're using up some of our reactant. So the change in concentration of A with a changing time is going to be equal to how fast our B is changing, right? So each time the reaction occurs, 1A goes away and 1B goes away. So our change in concentration of A is going to equal our change in concentration of B per unit time. Now, because our reaction here is going at 1 reaction per second, A is going away at 1 mole or 1 molecule per second. Right? So what we're going to see is that this value, how fast A is changing, it should be going down in value. Its concentration is decreasing. So our reaction rate is a positive number, 1 reaction per second. The value of A is going to be negative because it is going down. It started out at maybe 100 molecules. Then after the first second, it goes to 99 molecules, then 98 molecules, 97 molecules, and so forth. So the change in our value for A, it's going down, so it has a negative value per unit time. So to make it equal to our reaction rate, how fast the reaction is occurring, we will need to put a negative sign in front of it, right? And that's because our reaction rate is a positive value, but because A is going away, it is a negative value. Similarly for B, B is going away, and so it will also be a negative value. C here is being formed, right? So our C would be going up by 1 molecule per second under the rate that we have specified, right? If our rate is 1 reaction per second, then C will be going up by 1 molecule per second. So it would have the change in our concentration of C is going to be a positive value, and it will be going up at the same speed that A and B are going down, right? Every time the reaction occurs, you use up 1A, use up 1B, so these are going away at 1 molecule per second. C is being formed at 1 molecule per second. So the difference between C and A and B is that A and B are going away, and so they have a negative change in their concentration. Their numbers are getting smaller. C is going up in concentration, and so it will have a positive value. Now, a lot of times I like to add a plus here just to remind myself that I have balanced this and that it is going up, that I didn't just forget whether or not to put a negative sign in front. Now, the plus is not needed, the minuses are. So our concentration for D would be going up, so plus the change in concentration of D per unit time. Okay, so A and B go away at 1 molecule per second. C and D are being formed at 1 molecule per second. Now, if we change the rate of our reaction to, instead of being 1 reaction per second, to say that the reaction is occurring at the rate of 1 mole of our reaction per liter per second, right? Then what we would say is that A is going away at 1 mole per liter per second. B is going away at 1 mole per liter per second. C is being formed at 1 mole per liter per second. And D is being formed at 1 mole per liter per second. Now, this is all well and good, but most of our reactions don't have just 1 as the coefficient in front of each one of our values. If we look at something a little bit more complicated, let's say we're going to look at a similar reaction, but this time we're going to put some coefficients in front. So let's say we have 2a plus b goes to 3c plus d, right? So we're going to say that the reaction is occurring at 1 mole of our reaction per liter per second, right? So essentially we're crossing this arrow, 1 mole worth of reaction for every liter that we have each second. So what we would expect is that A, right, each time the reaction occurs and it's occurring at 1 mole per liter per second, A is going to be going away twice as fast, right? So our value, the change in our concentration of A is going to be twice as fast as our reaction. So our delta A, delta T is going to be equal to 2 times our rate, our reaction rate. Okay, and it's going away, and so it would be the negative of our reaction rate. Our reaction rate is 1 mole per liter per second. A is going to be going away at twice that, and so the value here, our value here would be 2 mole per liter per second. That's how fast A would be going away if the reaction is occurring at 1 mole per liter per second. Our value for B would be the same as the rate. So our change in the concentration of B with time, okay, would be equal to our rate. And then we would have a negative in front of B because the rate is occurring at 1 mole per liter per second. B is going away at 1 mole per liter per second because each time it goes across the arrow, 1B goes with it. Our value for C would be each time the reaction occurs, 3C are being formed. So the rate of formation, how fast the concentration of C is changing with time, is equal to 3 times the rate. Right? If the reaction is occurring at 1 mole per liter per second, C is being formed at 3 times that speed because each time the reaction occurs, we get 3C being formed. Our value for D would be the change in our concentration of D with time would be equal to the same as the rate. Now, what we can do, you can see that in each case, they're related to the rates, but it would be very convenient to be able to relate them to each other. So what we can do is we can rearrange each one of these equations that we're working with to make it in terms of rate. So what that would look like is for our first reaction, we would take and divide it by 2. Right? We would take both sides, divide it by 2. So essentially multiply by 1/2. Right? Over here, that will cancel out the 2, giving us negative 1/2. The change in the concentration of A per amount of time is equal to the rate. For this one, we would be dividing it by 1, and so it stays the same. For our C value, right, the change in the concentration of C with unit per change in time is 3 times the rate. So if we wanted to get it rate all by itself, we would divide both sides by 3. And so our 3's would cancel out. Our D, we'd be dividing by 1, and so we would get the same value. So if we bring these all together, what we would find, right, is negative 1/2. The change in concentration of A per unit time is equal to rate. Negative change in concentration of B per change in time is equal to rate. 1/3, the change in concentration of C over time is equal to rate, and same with D. We can bring these all together and get negative 1/2 our change in our A concentration, right, per unit time. This is equal to rate, and that is equal, because it's equal to rate and negative delta B, our change in our B concentration per unit time, is also equal to rate. They are equal to each other, right? If our expression here is equal to rate, and our expression here is equal to rate, then these two are equal to each other. So this is equal to 1/3 our change in concentration of C per unit time, and this is equal to our change in concentration of D per unit time. Okay, we can make a more general form of this. What I'm going to do is I'm going to erase all these different components, and then I'll show you the more generic form. Okay, now the more generic form is, let's say we have A components of A plus B components of B goes to C components of C plus D components of D, right? And let's say our rate is again 1 mole of our reaction per liter per second. So A is going away, so we put a negative in front of it. It's going to be going away at little a times as fast as the reaction is occurring. So this here is our rate of the reaction. A is going to be going away at whatever the coefficient in front of our formula is. It will be going away that many times faster than the rate. So to make our value equal to the rate, we would need to take 1 over little a times how fast A is actually going away. This would be equal to negative, because it's a reactant, 1 over B, our change in the concentration of B per change in time, which is equal. Now our C is a product, so it is being formed. So it would be plus, or you could leave out the plus, 1 over whatever the coefficient in front of C is, our change in the concentration of C. This is a big C over delta T, and that is equal to plus 1 over D, change in concentration of D per change in time. Now we can actually go in the reverse order of this. If we are given, instead of being given the balanced chemical equation, if we're given our changes, we can actually figure out what the balanced chemical equation is. So let's say that we had negative 1/2 our change in concentration of A, change in time, and that is equal to, let's say, 1/5 the change in concentration of B, change in time, and that's equal to the negative of the change in concentration of D per unit time, and that is finally equal to 1/3 our change in concentration of C per unit time. Okay, so if we look for the negatives, those are going to be our reactants. So the negative tells us that our reactants are A and D, and so our reaction would be, we take the coefficient, or the value in front here. This is 1 over our coefficient for the balanced chemical equation. So this would be 2A. It's a reactant because it's a negative. 1/2 tells us that the coefficient was a 2, because in our equations here it's 1 over the coefficient. Plus, the other thing that has a negative is D. It is negative 1 over 1, or negative 1, so our coefficient here is going to be a 1, and so it would be just plus D, goes to give our B value. Both our B and our C have positive values here. They don't have the negative, so they would be a positive, right? And so those are going to be our products. So 1/5 B means that it is 5B, plus 1/3 C means 3C, right? So you can go either forwards or backwards, and what you're looking for is the coefficient. The coefficients that you will find in your balanced chemical equation are going to be on the bottom down here, right? So this 2 tells us that we have a 2 here. The fact that we don't have anything on our D, we don't have a 1 over something, means that it's 1 over 1, and so our value here in front of the D is a 1, right? The 5 here and the lack of a negative sign tells us that this is a product, and that because it's 1 over 5, our coefficient in front would be a 5. Okay, so now there's a bunch of different things that are going to affect how fast the rate of the reaction occurs. The reaction can only occur when the reactants come together. So the higher the concentration, the more components you're going to have in a given space. The more frequently they're going to collide. And in order to do a reaction, they need to collide. So the higher the concentration, the faster the reactions are going to occur. The phase of the components also matters. So gases and liquid solutions are able to mix, and so they're going to typically react much faster than solids, right? If you have 2 solids, they're only going to be really able to interact at the interface between the 2 solids. So gas phase reactions and liquid phase reactions tend to be faster than solid phase reactions just because of how frequently the atoms themselves are able to collide and interact with each other. Intermolecular forces, both attractive and repulsive, can affect how fast the reaction occurs. If there is an attractive force, what that will mean is that your components are going to be pulled together and they will collide more frequently. The more frequently they collide, the more frequently they will react. If there are repulsive forces, that pushes them away, which will mean that they will react or collide less frequently, making it so that they react less frequently. So attractive forces will tend to increase the rate of your reaction. Repulsive forces will tend to decrease the rate of your reaction. Because the rates are affected by concentration, we should see this in any equation for rate. As the rates go up, what we should see is that the reactions occur faster. So if we have some sort of a mathematical relationship for how the rate is changing, most of the time it should have concentration somewhere in the equation. The general equation, what we're going to be calling it, is the rate law. The rate law is different from the reaction rate. It essentially is the mathematical expression that gives us the rate once we know the concentrations. So we have our rate here, and then the rate law is the mathematical expression relating the concentrations to the rate. There's a rate constant that's used to convert concentrations and take a bunch of other components into effect, like how frequently a particular collision gives you a successful reaction. So the rate law can be expressed as a function of concentration or pressure, depending on whether you're working under a solution or aqueous phase or in the gas phase. Although even if you're in the gas phase, moles per liter will still work. The units on K are going to change, and they change based on what the rate law is. Because the rate is always expressed as moles per liter per second, and you can have varying concentrations raised to different powers, the purpose of the rate constant is to help you get the correct units when you're all done. Now, for some reactions, the rate law, you could end up with rates of molecules per cubic centimeter per second. This is something that's seen in different types of gas phase reactions, particularly in the field of atmospheric chemistry. We look at molecules per cubic centimeter per second, but for this class, we will pretty much be sticking with moles per liter per second. Now, the rate laws themselves cannot be determined from the overall balanced chemical equation. They must be obtained from experimental results and or from knowledge of the individual steps in the pathway of the overall mechanism. The reason that we can't determine the rate law from the balanced chemical equation is the balanced chemical equation will give us an idea of the different components that could be in the rate law, but we won't know what these exponential forms are. Those exponential forms, those are what we need to have experimental data to be able to determine. When we know the rate, we can tell how fast the various components are occurring, but we won't be able to determine how varying the concentrations of our different components affect the rate without having our rate law. And the rate law itself is determined experimentally. Now, there is some additional information in the rate law expression. One of the things that we will be interested in is the order of the reaction. The order of the reaction is determined from the exponential values in the rate law, not from the coefficients in the balanced chemical equation. So the exponents are the m and n terms that we see in the rate law. Those are in the exponent here. We will often say, what is the order with respect to a particular component? So this m value here is the order with respect to A. So essentially, the order with respect to is the value that is in the exponent that is next to the concentration that we're talking about. So the order with respect to A is the value m. The order with respect to B is the value n. The rate constant is our K value. The rate law is the whole expression over here. The overall order of a reaction is equal to the m plus n. It's the sum of all your exponents. The order of a reaction does not have to be a whole number. These orders, you will find that you can have fractions, you can have negative numbers, you can have whole positive numbers. They are all perfectly fine. The values in these exponents will actually give you a decent idea of what's going on in the reaction, in the actual mechanism, what the molecules themselves are doing as the reaction proceeds. So, for example, negative numbers will typically indicate that some sort of a back reaction is occurring. Fractions often mean that you have something with two components or more coming together. Any one of these is perfectly normal, so the values don't have to be whole numbers. In fact, if we look at a bunch of different reactions, right, we can look to see what the various rate laws are. We will also see that for these reactions, looking at the reaction, we can't tell what the rate law is. So our column here is the various reactions. We have the rate laws and then the units on K. You'll notice the units on K change based on the rate law. So we can have what we will call zero order reactions, right? Reactions that do not depend on the concentration of the components. Those are perfectly normal, right? The value here, this would be NO2 raised to the 0 power. Anything raised to the 0 is 1. And so the concentration of NO2 disappears. For these types of reactions, ones that do not depend on the concentration of your reactants, a lot of times they're depending on something else. So these zero order reactions, as we will call them, a lot of times they will be things that are interacting with like a catalyst, a protein, an enzyme, or some sort of a surface. So for this one, this is the catalytic decomposition of NO2 on a nickel surface. So what's really dictating how fast this process can occur is how fast the NO2 can find an active site on the nickel surface. So it's really limiting how fast the reaction occurs is the nickel and not your reactant, right? And so the reactant doesn't appear in the rate law because it's really the nickel that's dictating how fast the reaction occurs. So for this particular process, the rate is equal to K, the rate constant. The units on K, because rate always has units of moles per liter per second, the units on K need to give you the units that you're looking for your rate. So the units on K will be moles per liter per second. For our next example, this is where the order would be equal to 1, so a first order reaction. You can see that here we actually have 2 hydrogen peroxide going to oxygen plus water. The coefficient in front of the hydrogen peroxide is a 2. That does not appear in our rate law, right? So our rate law, the order of the reaction has very little to do with the coefficients that you will find in the balanced chemical equation. So this is a first order reaction. We have concentration times K needs to give us units of moles per liter. And so the units on K will be just per second, 1 over seconds. right? So that would mean that our concentration, moles per liter, times 1 over seconds gives us our desired units of moles per liter per second. Looking down a little bit further, we see an example here of our particular reactant decomposing into methane and carbon monoxide. This has a fractional order, right? So fractional orders are perfectly normal. They occur all the time. There's nothing wrong with them. What that does to our units on K is you can see our rate needs to have units of moles per liter per second. So the purpose of K is to get rid of the extra units, right? This has 3/2 moles over 3/2 liters. You have an extra half mole, an extra half liter that you need to get rid of to get you your units of moles per liter per second. So the units on K will be liters to the 1/2 power on top over moles to the 1/2 power times seconds on bottom. We can have mixed units where we have here 3/2 and a 1. So what we would have is an extra 3/2 liter on bottom and an extra 3/2 mole on top that we need to get rid of from our concentrations. So the units on K would need to be 3/2 liter on top, 3/2 mole on bottom, second on bottom to give us our desired unit. Now you can have, like I said previously, the units on our rate laws, or the orders of our rate laws, they don't have to be whole numbers. They can in fact be fairly complicated. So for example, our reaction of hydrogen reacting with bromine gas to make hydrogen bromide or hydrobromic acid, this will give a rate expression of this. It's fairly complicated. This indicates typically that your reaction has lots of different steps. We have a negative value here. We have a 1/2. This is all over the place. This is a perfectly valid rate law. Okay, so we can actually come up with a way of expressing the units on K. So let's say we have our reaction, which is, or our rate law, which is rate is equal to K times A something to the M and B to the N. The units on K are going to be based on the overall order. So if the overall order, let's say that is Z, we're going to make that equal to M plus N. That's the overall order. For K, the units are going to be liters raised to the Z minus 1, moles negative of Z minus 1 times seconds. So essentially, whatever our value is, we need to leave us with liters on bottom, moles on bottom. So if we try these out, if our overall order is 0, then we would plug in a 0 here. We would plug in a 0 here, and so it would be 0 minus 1 would be a negative 1, so liters would be on bottom. Our moles would be the negative of 0 minus 1, that's negative 1. The negative of negative 1 is positive 1, that puts our moles on top. And then our units for our seconds, they would need a negative 1, right, because they need to be on bottom. This would end up giving us the units that we are after in the top case. If we look at here, a first order reaction, right, the overall order would be 1, so Z would be equal to 1. K, the units would be liters to 1 minus 1 is 0, moles raised to the negative 1 minus 1 is 0, times seconds to the negative 1, right? So that would give us L raised to the 0 is a 1, so it gets rid of the liters. Mole raised to 0 is 1, gets rid of the moles, and so we would get the units that we're after here. For something more complicated, like let's say this one here, our overall order would be 3/2 plus, we could do 2/2 to give us 5/2, right? Or 2 1/2, right? So to get rid of our extra units, we'd have 2 1/2 minus 1 would be 1 1/2 on top, or 3/2. The moles would be negative 5/2 minus 1, which would be 3/2, negative 3/2. And then here would be seconds minus 1. So that would give us the liters to the 3/2 times mole to the -3/2 times seconds to the -1. Right? So the key idea is that K is there to make sure that your units, when you're all done determining your rate, are moles per liter per second.